I'm Ryan. He's Arno.
I'm Arno. Hi.
Yeah, it's a kind of crazy title, but let me tell you a little bit about what it is that we do. Our job for PayPal, and we've been there for a long time now, is advanced technologies. So we're in charge of sort of looking at what we ought to be able to do 2 to 5 years from now as a company. It means that we get to play with a lot of crazy stuff, but it means that we get to play with a lot of crazy stuff that doesn't always work. So what we're here talking about today is actually some technology that we've been working on for the past couple years that underlies some of the real-time stuff that you might have heard mentioned in the introductions a little bit. So I'm going to let Arno run through the first couple of slides.
One thing Ryan forgot to mention is I'm on the west coast of San Francisco. Ryan's about an hour south of here in Fredericksburg. We've been telecommuting back and forth for we're working together 11 years. So we're kind of a connected device, two connected devices, sort of in a virtual environment. All right, so here's a scary slide. We've been talking about Internet of Things for a number of years. This is the scary slide because even yesterday, the fellow from Intel mentioned 50 billion devices. And I hope he was talking about 2020 and not 2014, which is where we are today. Personally, I think that this slope is actually not as steep as it should be. I think this is going to go parabolic in the next couple of years. For instance, this morning I read that Sylvania, Osram, the light bulb company, signed an agreement with Belkin Cable to do connected devices on light bulbs. So here's a company, an American company that's been around 100 years. Who would have thought they're going to change how light bulbs work? And they're basically going to be connecting light bulbs around your house, et cetera, et cetera. So this slope is going to be increasing dramatically. And if you're not ready for the data ingestion, the data analytics today, with the data that you have today, we're going to be swamped. We're going to be underwater with data in the next 2 to 5 years.
Well, so he hands off abstract and esoteric to me, so I'm going to walk through some of this stuff here. It's a pretty dense slide, but what we're talking about today is ontology and semantics, but not necessarily in terms of specifics about a particular event happening or piece of content. Rather, we're taking a step back and we're talking about describing description itself. And so in order to do that, we make a few assumptions here that I'm going to run through kind of quickly. The first one is that data grows based on producer content and on consumer need, and rarely, if ever, by general intent. So I can't think of a single instance where anybody said, you know, I think I'm going to create a data set for everybody for all the use cases at once, just because. I don't think it's ever happened. In fact, we hear lots of people talking about how unclean the data is all the time, that's one of their biggest jobs. Basically, though, it boils down to this. Producers generate data, which happens to be content in and of itself. And so a lot of the things that we get in IoT especially are data sets that have already been around, that have been sitting there. So they have a history, they have the actual content. They've been modified over time, but they still sit there in that original context. Whether or not that's normalized or structured or not, it's already there. Over time, they may make some performance optimizations for these, and they have the ability to leverage in situ adjacencies. This is where the case where you have, for example, a data set about a particular object, and then somebody else is like, well, we leverage that object in this other application, so let's sit all the tables for that right next to it so that they can access one another. So if you happen to be sort of nearby, proximity-wise, you get to be able to leverage that. And you tend to have local reference models for that. Consumers, on the other hand, they tend to design data access based on what they need it for. So let's say somebody's taking light from this room. They may care about lumens, they may care about direction, they may care about shadowing, but they couldn't care less about crystal in the chandelier. So when you gather that data set, if you are interested in finding out what kind of chandeliers were in here, all you're going to find out about is the light itself, right, which may or may not be there. That's kind of what all that stuff says. It also means that you generally have an application of some sort, whether that's a database or something actually written or a connected device or things like that actually understand, fill the blanks in, and give you some sort of comprehension. So you get a number back that's like 1800, it takes an application to tell you that that's lumens, and then probably takes a description in that application to tell you that 1800 lumens is roughly a 75-watt bulb, right? That kind of thing. The second thing that on this slide is that data acquisition and analysis requirements basically multiply each other's challenges. So what we mean there is for everything that you increase, especially as that parabolic curve goes up, any of the particular problems that come either from being able to acquire the data set in the first place or from being able to analyze it in the first place, amplify the other one, making the problem even harder, right? So for example, let's say you've got a data source that you want that comes to you at 100 times per minute, and now you want to start sampling it because all your light bulbs in your house are talking to you, and you're going to start getting 500 samples per minute, right? Well, that also means that the overall data set that you're looking at went a 5x larger, right? So not only are you trying to keep the time frame the same that you're acquiring the data, you've increased the size of the data set that you're trying to analyze in that same time frame, basically what we're saying there. The one thing that we want to call out that's really important for what we do is this bottom, the bottom side where it says parallel. Time parallelization is a huge problem when it comes to Internet of Things, especially, because whose time are you going to trust, right? Everybody has time, and that's the one thing that we've sort of relied on because it's sort of this constant we can count on here on Earth. The problem is all of the things out there think that there's a time too. Which one's right? Right? When you've got thousands of events coming to you at the same time from thousands of different sources, who got there first? Who sent first? You know, all that kind of stuff makes a difference. I'll boil through this one quickly because I spent too much time on that slide. But basically, I've got a quote here from Dr. Bell. She's an anthropologist who works in big data at Intel. But she says that, look, we need to start thinking about sensing technologies as devices that actually order our world, rather than devices that simply describe it. And once you do that, then you can get some really interesting social and technological understanding about what's going on here. And that's kind of what we're going to talk about with this ontology a little bit. So some things, some generalizations. But one, data holds context. It has information that you're after. Events also talk about context. They carry it, but they in and of themselves have meaning, and that is important, especially as you start to parallelize and get lots more data in. We have to turn our understanding then of not just the data, but also how we go about analyzing that on its head in order to be able to pull off things like real time, especially for real time at the kind of volumes that we're talking about. Remember, you'll see it here, the observation itself is an event. So it's not simply the fact that that there's a camera focused on me as I'm talking. I'm talking is an event. But the fact that that camera is recording at the same time is also another type of event. And it has different types of information associated with, both of which are important, even though the words I say are exactly the same in the same context at the same frequency every time I say them. And so finally, we need to augment things as they go, as opposed to relying on centralized data sets to augment our information. We need to augment as things are flowing by us within the sphere of influence that we particularly have as an observer. This will hopefully make more sense in a second. Do we really need another ontology to go about doing this? Because there's plenty out there. Yeah, we do, and I'm just going to sort of walk through this and see if I can illustrate a little bit why. You can't judge a book by its cover, but you can tell how much it's going to cost, right? There's two things going on there. The book itself is content, right? The cost is metadata that we would associate about the book. But the fact that the two have information which is different is still important, especially when you're going to try and codify and understand things coming at you at one time. Secondly, events themselves have to be captured as independent information in order to be able to understand what's actually going on. So if I say that this was the best concert I've ever heard, the event that most people will think right away is the fact that there's a concert. But you have to remember that me hearing it is also an event. If I wasn't at the concert, I wouldn't have heard it in the first place. The fact that I said it's the best concert when somebody else there probably left going, man, I can't believe I even paid for that, right? It's two completely different things, even though the event of the concert hasn't changed. So this kind of semantics about understanding what's actually happening in an event goes. Now, this has all been kind of abstract, so we're going to try and bring it back into the things that make sense by talking about this idea of sphere of influence here. And it basically boils down to this. The transmission of something doesn't just relay the information, but it orders and gives meanings to it. And that in and of itself increases the comprehension and the information itself that we gain. And it's important to keep both. It's always important to keep both, especially if you need to do stuff in real time. All right, you ready?
Yep. All right, so we talk about this sphere of influence. Everybody knows what a data lake is. It's a Hadoopish term for just massive amounts of data and files. We came up with a new term, or maybe it's not new, but we decided we'd call something a data sphere, which basically centers around an event that's in the center of the sphere, and there's both a temporal and a spatial aspect to the event as it happens. So as Ryan mentioned, different people can appreciate the event and experience the same event in different ways. As I mentioned before, I'm from the Bay Area. How many people here from the Bay Area? Great. So you know what happened 2 weeks ago? The Napa Valley earthquake. August 24th was a 6.0 magnitude earthquake, 3:20 in the morning. And we can use that as an illustration of the actual event that happened. So at T0, an earthquake happened, 3:20. There's no data generated at that earthquake at that point in time because there's no device there to read it. The device was a seismometer 2 miles away that was actually reading that event and gathering data. Now, in parallel, there's obviously multiple seismometers everywhere in the valley where this happened. I'm just going to illustrate with one event. But you have to understand that seismic waves rolling around the ground are hitting different seismometers at different times. So eventually, all that data has to be correlated back together to produce the proper maps for the USGS to actually analyze that data. So at time 2, the seismometer sends data up to the satellite. And what happens here is that event has transported data, changed the data to a message that the satellite can receive, and then the satellite basically beams it down to one of the ground stations where the data gets transformed again into human readable format with a lot of analytics. I'm really simplifying this, but the seismologists can actually see that this was a 6.0. So now we've had 3 events on the same, 3 different experiences of the same event, which happens to be the earthquake. And at the end of it all, we have a huge amount of damage, both economically and physically, to buildings and people getting hurt. And this is another event, but it encompasses a larger a sphere of influence, if you will. So we have wineries that are worried about the tourist industry, damage to infrastructure, et cetera, et cetera. I don't know how many people felt the event. If you're from the Bay Area, I luckily was on the East Coast at the time. But for me, hearing about it, 6 hours later, is also another event that I experienced because I wanted to get home to understand what kind of damage had been done. And the USGS has a wonderful website, and this is probably why East Coasters think that California is crazy, but they have a wonderful website where you can actually go and find out, did you feel it? And people can put in, based on zip code, if you felt the earthquake and how moderate, extreme, or whatever it was. So I quickly checked online when I was at the airport checking in to see if my zip code had felt the earthquake, and obviously it had, because I felt a 4.1 before out of Napa, and it wasn't the most pleasant experience. So one of the big things out of this, so we have 5 different times with the same event, data being generated. One of the big things that's come out of this is that since the 1989 Loma Prieta earthquake that happened, which is 25 years ago, this is the second largest quake or first largest quake that's happened since then in Northern California. In 25 years, the USGS has put out 400 more sensors into the ground, right? Our communication system is completely different. Everybody has a smartphone or a phone, cell phone. We now have video cameras everywhere. There's security cameras in businesses, in homes, et cetera, et cetera. But we have what we call an IoT phenomenon with wearables. So this is a graph that I pulled up from a blog by a company called Jawbone that has a wearable called Up. And this is a great analytics slide that actually shows you that people wearing these Up devices, wearables, the blue line shows you that people in the close proximity to the earthquake were woken up at 90%. 90% of those people woke up at the time of the earthquake or slightly thereafter. So it's basically a spatial and temporal analysis going on here, because people in San Jose, which is 100 miles away, didn't really wake up at all. And you'll also see that people in San Francisco, where I'm from, woke up and then went immediately back to sleep, whereas the people in Napa were quite concerned about what was going on. So the IoT wearables analysis for a particular event shows you that all this work can be done. So how does this relate back to PayPal? So Ryan and I have been working on a project for the last year, which we term systems intelligence. And systems intelligence basically is around how do we understand and analyze our ecosystem. And our ecosystem being our data centers, the applications in the data centers, the servers in the data centers, the interactions between servers and people, and all our IoT devices that are out there, which are basically our mobile apps on cell phones, our point of sales terminals everywhere on the offline world. So we have to understand how all those interactions occur. Now, we basically took 4 streams of data. Application logs, which we generate out of thousands and thousands of application servers, machine data out of the servers themselves, data center metrics like humidity, temperature, power, and social media. So we take all this information together and try to make sense of it and understand what happens when something happens like an earthquake event. How does that interact with everything that happens in our application and in our ecosystem? So we're doing this all in real time. Okay, we're very unique from all the talks I've heard today and some of the other talks and conferences that we've attended. We're fairly unique in doing this in real time. And I don't mean 2 minutes later. I'm talking within real time. So within milliseconds of what's happening. And the other problem that we're challenged with is, what are we up against in real time? Well, we're doing 3 million events a second today. Now, given that that parabolic curve is going higher and higher in the next few years, this number is going to be very astounding for us. I mean, it's a challenge as it is today, but it's going to get larger and larger. We're going to be doing 200 megabytes a second, which roughly translates to about 30 terabytes an hour of data ingestion and analysis in real time, 20 megabyte of machine telemetry data. There's 50,000 metadata relationships. We did this last year, and it's basically a graph of all the relationships together. It's not a psychedelic molecule or anything like that.
And it represents 1 hour of time that we're looking at in this particular.
And there's also obviously changes in social media happening here. People are on Twitter tweeting about PayPal. If we put out a new release, they'll either say, oh, that's great, or they'll say, well, this doesn't really work for me. So there's obviously changes happening in the social aspect. And of course, we've got an increased global customer service aspect to this as well. So we're basically taking all this data, ingesting it, analyzing it in real time, and try to make sense of it so that we can save on power. We can watch servers move up and down for power usage, because right now everything's on. It's the same with these light bulbs; they're on all the time. And from our perspective, Internet of Things inside the data center, for instance, we can actually start shutting down VMs and spinning them back up as the need for that application increases and decreases.
So, what we're going to show you here, I'll go through this quickly. This is the same exact thing, but from the perspective of one of the events that we actually have here. I'm going to go through it quickly. Basically, in this case, time zero is us releasing a new update to one of our features, for example. In this case, ACH transfers or transactions and buying generally. At T1, which is about a minute later, in this particular case, we see a spike in timeouts from connected devices around the world, whether that's swipe card things like Home Depot. It could be a terminal. It could be a HERE device. We also, about 10 minutes after that, detected an increase in IVR call volume coming into our customer service centers. And then our engine that's been correlating all this data here says, you know what, we've noticed that all of this stuff is relevant, and it goes back to T0, which happens to be this API release. And so we then automatically say, roll that code back, right? And then again, that happens to our command and control and orchestration system, so that by the time at T3, we've already understood what was going on. This was a process that could take actually literally days, sometimes in the past. And we've been able to get it down into real time. T1 and T2 in this particular case take longer to occur, but our understanding of what's happening in T3 is actually done in 250 milliseconds or less. And then we're able to affect that rollback so that within about a minute and a half of having detected the rollback, the need for rollback, we've actually pushed the code back to get things off. This is a little bit about the actual ontology itself. It's really hard to read, and we don't have a whole lot of time to go through it. But basically, I define 4 different things here, and I'll just get to a slide with them all on there. We have a concept of scope, which is probably the most important. It defines things like whether you're an element yourself, whether you're an event, a particular node. A pool for us is just a collection of nodes. A pod, a point of deployment, is a collection of pools. And global means everywhere in the world. So basically, it's your reference idea. And then by combining latency dependency and what we call impacts, you can describe any event in the world, whether it's an earthquake event like we talked about before, or if it's a case of, in this particular case, our application invoice web is actually connecting to a database here, is what you see. It's not an error message. This is an OK thing that happened. We get them all. It's important, though, I think, to realize that as we go through this, the idea that I think is central to what we're trying to do is by taking a step back from the actual data, from taking a step back from trying to clean it up and make it tell us what we think it ought to tell us. Because I think that's one thing that data analysts bring to the table that they sometimes forget about. You have a question in your mind you want an answer to, and therefore you're bending your will to the data set. In order to be able to understand a truly parallelized IoT world, especially one that you can't predict with information coming from all different sources, you have to take yourself out of that equation, at least in the data acquisition phase, especially if you want to do things in real time. Because you simply don't have time to go, well, maybe if I bring in this other data set over here, I can augment that. Or you know what, if I clean this up so that it fits nicely into this little bin, it'll tell us. I don't know if you notice, for example, most of what we do here is simply hashes of information, right? Because we realized at the end of the day, the machine learning was correct. It figured out the right thing. We people care about what it actually said. Computer couldn't care less. So for us, the hash is absolutely just as good as the original data, and it's an awful lot faster. And so that's kind of what we're bringing to the table. You can get more about it. These are all the different types of event scenarios. I don't have time to go into the specifics, but you can ask a question about them if you want. That they can cover. But by doing this, by taking this sort of second order approach and redefining how we think about data and how we codify it as it flies past us, we may have a chance at being able to comprehend what's going on in IoT. But as long as we're leaving stuff in a data warehouse somewhere, we've already lost. That's it. Thanks.
Thank you.